This is lecture 3 and part 1, visualizing Qubits, the block sphere. It's easy to visualize the state of a Shannon bit. It's simply two disjoint points, perhaps in a lattice. But how do we actually visualize the state of a qubit? So far we've thought of a single qubit as a vector in a two-dimensional complex Hilbert space, but this is actually not fully correct. Let's let ket psi be an element of our Hilbert space H. Actually, for all complex numbers lambda different from 0, lambda times that state represents the actual same physical quantum state. Because the reason for this is the global phase is not physically detectable. And since these represent the same state, the actual state is a complex line in the Hilbert space through the origin. That is actually the state of the Hilbert space. The space of all complex lines to the origin is a well-studied space. It's called complex projective space, denoted by CP1. In photography, for instance, they work in a real projective space. Here, and for qubits, we're working in complex projective space. We now are going to show how to visualize the qubit state space, CP1, as simply the surface of a ball, a sphere. Consider an arbitrary chosen state. Here it is, ket psi. You can think of it as a column vector of two complex numbers. For the time being, let's assume that the amplitude of ket 0 is not equal to 0. Then the state is equivalent to the state so shown, where B over A is a complex number of the form S plus IT, where I is the square root of -1. In this way, the state of the quantum system corresponds to just a single quantum complex number. If A is 0, we'll simply say the state corresponds to the point at infinity. So the state space of a qubit can be identified with the complex numbers plus the point at infinity added. And let's see if we can look at that. So in other words, if we look at the standard basis, ket 0 is identified with the complex number 0. Ket 1 is identified with this number we call infinity. And we have the ket plus basis. Ket plus is identified with 1 and ket minus with -1. And another orthonormal basis, we have identifications with I and -I. And in general, of course, we identify each ket with the complex number B over A. And this is easy to visualize in the complex plane. Ket 1 corresponds to the point at infinity. Here's ket 0, corresponds to the origin. Ket plus corresponds to 1 in the complex plane. Ket minus corresponds to -1 in the complex plane, and so forth. And of course, we have the point at infinity, and ket psi corresponds to a point at location S comma t in the complex plane. The next thing we're going to do is we're going to do a reverse stereographic projection. And we simply can identify each point in the complex plane with a globe or a sphere. In this case, the sphere is intersected by the complex plane at its equator, And each point in the complex plane is identified with a point on the sphere by simply drawing a line from the point the point in the complex plane to the North Pole. That line intersects the sphere at a point, and in this way we identify the point A over B with ket psi. As ket 1 is the North Pole, ket 0 is the South Pole, ket minus is on the equator on the left, and ket plus 1 is on the equator to the right. Thus, the state space of a qubit is actually a sphere, which we call a block sphere. Now that we've learned how to visualize a qubit, what about more than one qubit? Can we visualize the state space of 2 qubits, of 3 qubits, and so forth? The answer to this question is not so simple, but let's take a brief look at it. I'd like to talk about what is called multi-partite systems, that is, systems made up of many quantum systems made up of many qubits. We'll define a multi-partite quantum system, Q, as a system that consists of qubit systems denoted respectively by Q sub 0 to Q sub n minus 1, each having respectively a two-dimensional Hilbert space H0, H1, Hn minus 1. And the Hilbert space of the multipartite system, made up of all the qubits, is simply the tensor products of the respective qubit state spaces. If the set consisting of ket 0 and ket 1 is designated as a standard orthonormal basis of Hj, then these bases induce a standard orthonormal basis ket 0 up to ket n minus 1 for the n-qubit space noted by calligraphic H. In other words, each orthonormal basis element is the tensor product of tensor basis elements of single qubits. The state of ket psi of a general element, the general space, the state of an arbitrary ket in the state space of our multipartite system can be written in the following form in terms of the standard basis, where the Z0, Z1, Z2 to the n minus 1 are the amplitudes, the complex coefficients. Notice that it's easy to visualize the state space of a classical bit, of n bits in fact. And here, this is basically the state space of one classical bit, 2 classical bits, and 4 classical bits. This is because the state space of Shannon bits is simply the space of all binary n-bit strings. Now, for classical bits, please note that the number of states for such a multipartite system is big O of 2 to the n, and each state can be described by a binary string of big O of n classical bits. On the other hand, for qubits, the state space of a multipartite quantum system is far more complex and more difficult to visualize. How do we visualize the state space of n qubits? As you'll see, it's not so easy. Let's let ket psi be written as a complex linear combination of the standard basis elements, be the expression as so shown. Let's let ket psi be a typical element in this space, and we've written it as a complex linear combination of the basis kets with amplitudes Zj. We can break up the set of such states into disjoint sets. First, we consider the set of all states with non-zero zeroth amplitude. In this case, such states are the same as the one indicated here. We divide by Z0, and those can be identified with n-tuples, 2 to the n minus 1 tuples of complex numbers. If Z0 is equal to 0 and Z1 is not equal to 0, we have another disjoint set, then the state can be identified with the 2 to the n minus 2 tuples of complex numbers and so forth. And now if we piece together these parts of the state space, we see that it's the union of all 2 to the n minus 1 complex n-tuples with disjoint union with the state of all 2 to the n minus 2 disjoint tuples and so forth. The highest dimension here is the first part, consisting of 2 to the n minus 1 tuples of complex numbers, and the dimension of that is, as a complex space, is 2 to the n minus 1, but as a real space, it's twice 2 to the n minus 1. And the whole state space of a qubit can be shown to be certainly not a manifold. It's a very complex geometric structure. So now we can see that the state space of, say, just 2 qubits is 6-dimensional. The state space of 3 qubits would be 7 times 2, 14. These spaces are indeed difficult to visualize. There has been a great deal of work on the state space of 2 qubits. That's as much as I'd like to say about visualizing n-qubit state spaces. What I now like to turn to is measurement, both classical and quantum. Measurement is one of the hardest things to learn for newcomers in quantum mechanics. I'll try to make it as simple as I can. Now I'd like to talk about measurement of just a single qubit. Then we'll move to n-qubits later, and finally we'll move to the full protocol for measurement in quantum mechanics. Measurement with respect to a qubit is with respect to an orthonormal basis. So for the time being, let's choose the standard basis as our orthonormal basis. Recall that if the qubit is of this form, it can be written as alpha ket 0 plus beta ket 1, and if it is measured with respect to the standard basis, one of 2 possible outcomes will happen. With probability magnitude of the first amplitude squared, we'll see ket 0. With probability magnitude of the second amplitude squared, we'll see ket 1. In quantum mechanics, we cannot control the outcome of a measurement. We can only predict probabilities of outcomes. We, of course, have to do this. We have to assume that ket psi is of unit length. Otherwise, the following scheme is meaningless. In other words, we choose our ket such that it's a vector of our ket of length 1. Now, we made a measurement with respect to the standard basis, but there's no reason why we couldn't choose any other orthonormal basis. So in this case, I'll define another basis called ket plus and ket minus. This is a basis that occurs if you apply the Hadamard transform to the standard basis. And ket plus and ket minus are defined as shown on the slide. And once we do that, we need to re-express our ket not in the standard basis, but in the new orthonormal basis, and that's what is done as so shown. And then when we make a measurement with respect to this basis, we see ket plus with probability magnitude of the ket plus amplitude squared, and we see ket minus with amplitude of ket minus squared. Let's not stop there. Let's choose another orthonormal basis, ket I and ket minus I, and make a measurement with respect to that. Ket I and ket minus I are defined as so shown. Once again, what we'll do is simply re-express the state of our system in the new basis and use the corresponding amplitudes to compute the probabilities of outcomes of when measured with respect to this basis. Now let's look at classical versus quantum measurement. And we'll do this in terms of the measurement of flipping a coin. When you flip a coin, you either observe heads or tails, so you can think of that as a form of measurement. The previous three measurements with respect to a basis demonstrate very emphatically how qubits differ from Shannon bits. We can see this with an example. Consider a classical coin which, when flipped, thus observed, produces heads H or tails T with probability as so indicated. And of course, since the coin comes up either heads or tails, the sum of the probabilities is 1. Now let's compare the classical coin with a quantum coin, a qubit. What we'll do first of all is that we see that we can measure the coin, flip the coin, by measuring with respect to the standard basis. So unlike the classical coin, the qubit behaves actually in at least 3 different ways, depending on which of the 3 bases we choose to measure it by, to observe it by. And let's see where that leads us. It leads us to the following diagram. A qubit, in a certain sense, behaves like more than one coin. If it's measured with respect to the standard basis, you have one type of coin. If it's measured with respect to the plus-minus basis and other, and so forth. In fact, there are as many coins as there are bases. Of course, there's an interesting topic here that maybe I'll touch on. Some of these observations are independent and some are not. What we've seen is a qubit behaves like many different coins depending on how it's observed. If in the same vein we continue to pursue this, but now for 2 qubits or more, we encounter some amazing non-classical behavior, which is beyond these lectures, the Bell inequalities. Perhaps in another lecture we'll see that. There's much more to measurement. What I've tried to do is to approach measurement gently on a step-by-step basis. First, measurement of a qubit with respect to an orthonormal basis. The next thing we could do is measure in qubits with respect to corresponding orthonormal bases of n-qubit state spaces. And the final step in understanding quantum measurement is measurement with respect to the eigenbasis of a Hermitian operator, also known as an observable. I'm stating these facts because step 3 is beyond what can be said in this lecture. I'm saving it for a future lecture, I guess. But I'd like to give you an indication of step 3. In step 3, the entire process is measurement of an observable which is represented by a Hermitian operator kappa omega. And the state being measured is denoted by kep psi. That's our quantum state of our quantum system. What we're going to do is make a measurement with respect to the eigenbasis of kappa omega. What happens inside this box when we're making the measurement is unknown. We'll leave that to philosophers. But what happens when we measure our system, we see in the device that reads the output an eigenvalue of the observable, and unseen to us, in the quantum world, the state immediately moves to a corresponding to the eigenspace corresponding to that observable, and this all occurs with probability given by the direct bracket notation, where I've now used the spectral decomposition of the Hermitian operator omega. And now you can see why I have not spent too much time talking about more advanced quantum measurement. Let's continue now and talk about ways of programming quantum computers, wiring diagrams. Recall, as previously mentioned, there are two types of quantum instructions for quantum computer programs. There's the unitary transformation U, where U is unitary. If it's conjugate transpose, its adjoint operator, the dagger, gives you the inverse matrix. Another definition is that these are the matrices that preserve the length of our kits. The second type of instruction is a measurement, which can be far more complicated in its mathematical description, and this is given by Hermitian operators as indicated in the slide I just showed you previously. However, now we're going to run into a problem in regard to programming a quantum computer. As the number n of qubits grows, the size of the matrices U and omega grow as 2n times 2n. They grow exponentially. The question is, how do we program a quantum computer when the size of our instructions, our computer program, are growing as big O of 2 to the n? The answer is to represent quantum computers as wiring diagrams, which grow as big O of n for n the number of qubits. In a sense, the language of wiring diagrams is analogous with today's classical computer languages such as C, C++, Python, and so forth. Of course, what is a wiring diagram? A wiring diagram consists of lines and gates. A solid line corresponds to a qubit. A double line corresponds to a Shannon bit, a classical bit. A solid line labeled by an integer and a slash denotes n qubits. Gates correspond to quantum computer instructions, that is, the unitary transformations and measurements. Here are some examples of gates. We have the Hadamard gate we've seen before. These are single qubit unitary transformations. The Pauli spin operators x and y. The single qubit gates also, the last Pauli spin operator z, the phase gate, and the pi over 8 gate. And that's called pi over 8 because that's, if you look at the rightmost entry in the 2 by 2 matrix, that's e to the 2 pi over I over 8. Here are some 2 qubit gates. The controlled NOT, the swap, simply swaps the qubits, and a controlled Z. Of course, what do I mean by control? In quantum computing, we control gates. The dot indicates the control bit, qubit. The object here is the target, which is being controlled. And essentially, this says that when the qubit on the top line is 0, then the gate on the bottom line is the identity unitary transformation, does absolutely nothing. On the other hand, if the qubit at the top is a 1, then essentially this gate is executed on the second qubit. These are controlled operations. We can form any kind of controlled U operation. And this can also be thought of as a controlled X gate. X is really not. It flips bits, so it is a not. There's a controlled flip bit I mentioned, controlled Z gate. Then we have some 3-qubit gates. The Toffoli gate, a very famous gate in reversible computation. This is a doubly controlled NOT, essentially. Both qubits must be 1 for an action to happen on the bottom qubit. The Fredkin gate is a controlled swap. That's basically what it is. Okay, and finally we have the measurement gate, which is indicated by a small meter, and it performs measurement of a qubit with respect to the standard basis. As we will see, this is the only measurement gate we need. All measurements with respect to other bases can be made by inserting unitary transformations before this gate. In general, a wiring diagram is of the form shown here. It has a series of gates, and at the end, of course, unshown are the measurements. Please keep in mind that gate A0 is applied first, the unitary transformation applied first, and AN is applied last. So when you write down the matrix representing this, we reverse the order of the operators as so shown. This is a common pitfall for students just beginning to learn quantum computing. Here's an example of a gate. Let's consider the following wiring diagram. This is the Hadamard transform applied to the first qubit, then followed by controlled NOT. If we write this as matrices, once again we use reverse order. This is C naught, and the gate H is really H tensor I because nothing is done to the second qubit. So this is a product of C naught and H tensor I applied to the input state, which is ket 0 tensor ket 0. And here below I've made the calculation, or started to make the calculation, for computing psi, the outcome of the gate when the ket zeros are put in as input. If we continue this calculation, I basically just computed the tensor product of H with the identity, and then we multiply the matrices, and we end up that this produces what is known as the Bell state. This actually produces an entangled state. A lot can be said about the Bell state, but we'll save that for later. As an exercise, I'd like to suggest that you show that these two wiring diagrams represent the same unitary transformation. You can do this in many ways. One way is simply to compute the matrices as I mentioned before, the product of the matrices corresponding to each one of these diagrams, and see if they're the same. A much simpler method is to use a theorem in linear algebra. Two linear transformations are the same if they agree on the basis elements. So all you have to do is verify that these two diagrams do the same thing on both basis elements. Another exercise is the following. The leftmost wiring diagram represents the application of the Hadamard transform first to the second qubit, and the Pauli spin operator second on the first qubit. The second wiring diagram represents the opposite, applying X first and H second, and finally the third applying both gates at the same time. They're all physically different, but essentially they produce the same unitary transformation as indicated by the expression below. There's much that can be done with wiring diagrams. Here's an example of a wiring diagram that produces the Bell state and then makes a measurement of the 2 qubits of the Bell state to produce the following probability distribution. In fact, the Bell basis is an orthonormal basis that's used quite frequently in quantum computing, so let me just mention what it is, and here it is as so shown. And one interesting thing about the Bell basis is that one can move from one Bell basis ket to another by an operation on only one qubit, say the left qubit, as done in this fashion. So if Alice owns one qubit and Bob owns another, and they're separated by a great distance, Alice can change the entangled state they have by performing local operations. And here's the formula for that. A lot more could be said about this, but that would be for another course. And I should say, we can move from one Bell basis to another, I've said this before, by applying a local unitary transformation to the left. And later on that can be used for different protocols. As an exercise, please, I'd like to suggest you take time to verify that the formulas I showed on the last slide are actually true. Actually compute it using matrices. Here's an example of another wiring diagram where we have controlled the unitary transformations with the gates. We control the gates with classical information, as so indicated. And actually, this wiring diagram is an implementation of the formula I showed you on a previous slide. Verify that the following wiring diagram does the following. I'll leave that as an exercise. So essentially what this diagram does is transform the standard basis into the Bell basis. This is another wiring diagram which transforms the Bell basis back into the standard basis. All I had to do was move the Hadamard transform from one side of the wiring diagram to the other. In this case, this is a wiring diagram with measurement added. Classical bits are 0 and 1 are output by the measurements. Probabilities are computed in this way. Next, what I'd like to do is to talk about QUIRK, which is an online useful wiring diagram simulator. And why don't we do that? We're now in the routine QUIRK on the web, and there, as you see, there's documentation as to how to use the simulator, a video tutorial. If you'd like, you can play with the source code, and you have many different examples of quantum protocols and algorithms and whatever, and we'll take a look at that in a second. But let's go to Edit Circuit. As you see, at the top and the bottom are your different gates that can be used to design your circuit. A circuit can be designed by simply dragging a gate or other object into the circuit. Let's see what we can do. Let's drag a Hadamard transform in, and now you can see the block sphere for the qubit corresponding to the first line is pointing into the ket plus direction. If I were to change the 0 to a, see if I can do it, a 0 to a 1, if I were to change the 0 to a 1, immediately the Bloch sphere points to ket minus. Let's create a controlled knot. And we see that from this box, this is a measurement box, but a theoretical one. There are two types of measurement boxes in QUIRK. One is an actual measurement. The one is a theoretical measurement. It's the measurement that would occur if you were to measure it at that point, but it does not disturb the dynamics of the circuit, whereas the first measurement I pointed to is a classical measurement, a real measurement that actually distorts the dynamics of the circuit. One thing to see immediately is you'll notice that we're getting no information about the qubits from the Bloch spheres, and the reason for that is the state generated by this wiring diagram is an entangled state. That means that the state of each qubit is indeterminate. If we were to remove the control knot and just work with an X gate, you'll see that the states are well defined on the Bloch sphere. If you look at the blue circles, they represent amplitudes. The one on the left is the amplitude of ket 0. The one on the right is the amplitude of ket 1. The radius of the circle is the magnitude of the amplitude. The position of the line drawn from the radius indicates the phase of the amplitude. So this is a polar representation of the amplitude of ket 0 and ket 1. There are time-varying gates. There's the, essentially you can take x to the t, so where t varies with time. If t is a half, you get the square root of x as a circuit. If it's a half, the fourth root. So let's put that in there. And now we see that the first Bloch sphere is varying with time. Let's see what we can do if we put a control operator on there. We no longer see what's happening, but the amplitudes are actually changing with respect to time. Let's go back to the menu itself, and let's take a look at quantum teleportation. And let me simplify this teleportation a little bit. There are too many qubits here. It's going to interfere. Let's move things around a bit. The dotted lines just do nothing. All right, so this is a quantum teleportation circuit. The top wire represents the qubit to be teleported. The bottom two wires correspond to the EPR pair that's created by Alice. At this point, we have an EPR pair created. And now Alice is going to measure the first two qubits, and this sequence of gates that I'm circling with my cursor is really a Bell measurement. We're making a measurement with respect to the standard basis on these qubits, but if we prefix our measurements by unitary transformations, this is effectively a measurement with respect to the Bell basis. Now what happens, the information that Alice gleans by reading or observing her qubits would be essentially 2 bits of information which are sent on to Bob at another location. Bob immediately uses that information to apply local transformations x and z, depending on what is received, A and B, to transform the circuit back into the original qubit state. Now, one thing to remember at this point is by the time Bob receives his qubit, fully recovers his qubit, the original qubit has eventually been destroyed. It has to be because of the no cloning theorem. I guess we can play around with this. Let me take out the circuits which is generating just a time varying qubit. Let's take it out for the time being. And let's put in a Hadamard transform. Well, let's change the input qubit to a Ket1 and watch the two block spheres. Immediately the qubit, the top block sphere is pointing in, has a point that moves in the bottom direction, and so does the other. And both block spheres are moving together. Let's see, let's change this to another state, Ket minus, different positions. And if we go to Ket plus, we have different positions on the block sphere. This is beautifully done. Much more can be done with this simulator. So let's create a circuit. We could create a time varying qubit by using x to the t. Now you'll see that the qubit is moving around the block sphere. X to the t varies with time t, and as if t, for example, is a half, x to the t is the square root of t, and so forth. All the roots of the Pauli spin operator are varying with respect to time. The amplitudes are shown to the right by the blue circles. The first blue circle on the left represents the amplitude of Ket 0. The second represents the amplitude of Ket 1. The blue circles really are a way of representing the polar representation of the amplitudes. The radius of the circle is the magnitude of the complex number, and the line emanating from the center of the circle represents the phase of the amplitude. You'll notice a box here is changing with respect to time because our qubit is changing with respect to time. It gives the percentage of times that the qubit is 1 when measured.